Swayam Prabha. Digital India. Educated India.
Good morning, everyone. After the wonderful introduction session from Professor Rajanambat, I don't need much of a time to get through the fundamentals, but still I will quickly walk through with what I have made, adding few points with whatever he said. In fact, you all know now how to define corrosion. If I ask you to define corrosion, how will you define corrosion? Degradation of materials. Is it complete degradation of materials alone can be said as corrosion? Okay, if you say interaction with external environment, what kind of interaction? Chemical? Is it only chemical, or is there any other process which is involved, especially for metals? Dry and aqueous. Okay, in that aqueous corrosion, if you say about if it is only chemical, is there anything different? Electrochemical. What is the difference between chemical reaction and electrochemical reaction? There is a flow of charge, or there is transfer of electrons which leads up to charge. So when you talk about chemical reactions, we all know that if I want to know the feasibility of a particular reaction for a particular case in terms of chemistry, I'm going to talk about free energy change or Gibbs free energy change. But if I have to specifically talk about an aqueous system, especially for metal systems in environment, we talk about this as a physical and chemical interaction of the material with the environment, and this interaction can be chemical, basically chemistry, but it's little more specific, it is electrochemical in nature. That means there is going to be flow of charges, there is going to be separation of charges on the surface, and therefore you're going to have some phenomena related to it. If I say chemistry or chemical reactions can be related to free energy, as Professor pointed out, the electrochemical reactions, especially when you bring in water or moisture or atmosphere which containing moisture, you're going to talk this not in terms of free energy, we are going to talk in terms of potential. Why did we try to talk in terms of potential? It is measurable. Okay, why not? I can give it, for example, at a high temperature oxidation of titanium in the presence of oxygen at 800 degrees, I will give you a value of change of free energy is minus 234 kilojoule per mole. Based on the negative sign, minus 234 kilojoules, it can be at 900 degrees, minus 400 kilojoules per mole. So at 900 degrees, more the negative, more is the magnitude, more easier it is to form the oxide. But that doesn't mean it will form the oxide. So I can still talk in terms of delta G. Why did I move to E or potential? Measurable is correct point. Is there any other reason why the potential, where does that potential come from? Charge transfer. So when I look at an interface of a metal with the environment, we say that there is an interaction, and that interaction is electrochemical in nature. Since we talk about charge of transfer, the surface is not neutral. The surface has certain charge in vacuum, and when you bring it to the aqueous environment, based on what happens to the metal surface, there is going to be a kind of an alignment or arrangement of these charges which leads to a difference which is developed at that electrolyte interface, which we call it as electrified interface. And that electrified interface has an inherent associated with potential, which you now related with delta G, and that potential can give you an idea about how fast or how feasible the reaction is, or how feasible or how tough the reaction is to happen. Now if I say you a word, corrosion is surface driven process. From mechanical engineering, can you say what is another process? Which wear friction. If I say corrosion is surface driven, what comes to your mind? Why do I say this thing? It is a surface with which interacts with the surface. Why it has to start from the surface? What is so inherent that it starts interacting? It is exposed, wonderful, but is the exposure only reason? Basically the surface, the energy associated with the surface is much more. Why the energy associated with the surface is much more? Because you have broken bonds, therefore you have energy higher, so it is easier to start with the surface. Then asking the question which he asked in the previous session, is all surfaces the same? So if I talk for an engineering student, if I say surface, it's a polished surface, but if I look closer into the surface of mechanically polished, I look closer into the surface using appropriate characterization tools. Let's say I'm using a scanning tunneling microscope or an atomic force microscopy, I should be able to see surface as not as a mechanical engineer looks or as a metallurgical engineer looks. Just from the top, you look at the surface, you have multi steps basically, which is called as, this is one terrace and this is the second terrace. And if you look in that terrace also, there are arrangement of atoms in a certain way. And when you talk about arrangement of atoms, it is possible that is one surface add atom which is present on a terrace and it is attached from only one side. Some places where you have an atom missing from the surface, it is called surface vacancy, and this is what we call it as a step. And the surrounding atoms around the step are coordinated in a certain way. So every surface is heterogeneous in nature. If, for example, this is a metal which has to dissolve in an electrolyte, the first one which would get down is the add atom. Do you agree? Why? It's more surface area to interact with the electrolyte, the add atom, because it is attached from only one side. So no matter what you do, as perfect as we say it as an atomically flat surface, not a mechanically flat surface, even an atomically flat surfaces have heterogeneous sides where you have the initiation of a corrosion process, and then corrosion process progresses further into the deeper layers. That's why I say corrosion is a surface driven process. Okay. Now I established that it's a surface driven process. I need to also say you that it is also dependent on the environment. As professor already pointed out, you can use a particular metal in a particular environment. For example, here in case of copper, if you put it in sulfuric acid, it basically dissolves in the presence of an oxidizing agent. But the same copper, if I remove the oxidizing agent, especially the aerated condition, you remove the oxygen, the copper is inert. But stainless steel is reverse of it. Why? The stainless steel will dissolve if it is in deaerated acid, but it does not dissolve in aerated acid. The reason is because, what is the reason? How does stainless steel become stainless? So basically this stainless word comes because of the formation of an oxide on the surface. So in order to form an oxide in deaerated conditions, you do not have sufficient oxidation power to produce the oxide. So I need a solution which contains an oxygen, especially stainless steel will become passive if and only if you have sufficient oxygen or the solution or environment is aerated. Now, this is just to remember yourself what is a reducing agent and what is an oxidizing agent. In our case, the metal is the one I always keep it as reducing agent because that's the one which likes to give the electron, and the species which is in the environment, it could be oxygen, it could be proton, it could be chlorine, which are the ones which can pick up the electron, they are the oxidizing agents. This is just a revisit to the concepts of it. Now, as professor pointed out, you also saw that there are various kinds of, on a particular case, he simulated or gave an analogy to the electrochemical cell, that's basically a battery, to a corrosion system. What are the major salient points which you saw in a battery? If I open up a 1.5 volt battery, what do you see? If I rip it off, what will be the center part? An electrode, that's one, is a graphite electrode, and then surrounding that you will have what? A moist layer, which is a paste, which could be manganese oxide, that is the function of electrolyte. And then what you have is an outer case which is basically made of zinc, which is basically an anode. So if you look at this, this contains an anode, a cathode, and in between electrolyte. So two electronic conducting medium in an ionic conducting media comes up into a corrosion cell. And this is how, because of corrosion, you get a certain voltage out of it, it's 1.5 volt. The same is what happens when you have a surface of an alloy exposed. At one part of the surface, I'm going to have an anodic reaction possible. That means it is one giving electron, and other part of the surface, it's going to be a cathodic site where some species is going to pick up that electron and reduce onto the surface. So if I take a surface, I will always have an anode and cathode. Based on where the site is, if I am able to distinguish between the anodic and cathodic site, then I am going to say this form of corrosion will be a localized corrosion. But if there is no separable anode and cathode or undistinguishable anode and cathode happening all over the surface of the metal or the alloy system, then we say this system will undergo uniform corrosion. Normally, if I ask a student what is uniform corrosion, they will say me, sir, this is removal of material over in a uniform fashion over a period of time. But the scientific aspect behind this, it is something to do with the anodic and cathodic sides. If you are able to distinguish among these two, then you're going to see still corrosion is there, but it will be in a localized form. Can you say me one localized form of corrosion which comes to your mind immediately? Pitting corrosion. Why it is a localized corrosion? Okay, I will give you an example. Have you ever seen people storing salt at your home in kitchen? People storing salt in a steel container or a stainless steel container. It will corrode. Have you ever seen that corroded utensil? Have you ever seen it? What is the corrosion which you see on the surface? Do you see it as a rusty layer which is on an old rust car, which is located at a very long time being kept out in an environment, or it is still shiny, but there are certain locations at which you see events of corrosion? So those parts which you see at certain locations basically says something is inherent with stainless steel. That's the growth of oxide on top of it, which makes it stainless, and that oxide is typically chromium oxide. And because of the presence of chloride from the sodium salt which you use, sodium chloride, you have at certain locations basically the oxide has been broken and you have corrosion happening at a local spot. Now on the same stainless steel utensils, where if you would have kept in a normal conditions, you would have anode and cathode at indistinguishable, inseparable, but somehow you now have a separable anode and a cathode. Therefore you see one position alone corroding, the other is well protected. Therefore you saw spots at different locations on the surface of the utensil. So this difference is what gives you to identify the form of corrosion into two. One is called as uniform corrosion, another is called as the localized corrosion, and pitting is one of the example for localized corrosion. Now, have you ever heard rustless wonder, iron pillar? Who said? Iron pillar. Why iron pillar in Delhi is called as rustless wonder? Basically, Delhi iron pillar, the history behind it is this, that it's standing from 375 to 413. It's close to 1600 years in history. Even today, if you look at this through the structure from the bottom to the top, you can very clearly see what is the inscription written into it. Today's generation of steels do not provide this luxury, but this Delhi iron pillar withstands the corrosive environment of Delhi, which is cyclic cold or cyclic wet and dry cycles, winter and summer cycles, which leads to a specific conditions. Therefore, the Delhi iron pillar stands as it is without rust. If it would have been a normal mild steel, this would not be visible in 1600. You would have seen that it will just flake off and then you will spall off. You will see nothing at that location. But this Delhi iron pillar stays close to 1700 years, and that's what we call it as rustless wonder. Why it is happening? The reason is because when they produced this, they used a technique which is called hot forging, and when the raw material of iron which is used, it was containing phosphorus in the system. And when phosphorus was, could be a serendipity or could be intentional, still it's a questionable factor. Because of the presence of phosphorus, we all know that iron, from thermodynamical aspect, by nature it has to become iron oxide. But since you added phosphorus to a certain amount on top of it, you had an interlayer which is iron hydrogen phosphate, which is crystalline in nature, and that separates the base metal from the rust layer. If this phosphorus would not have been present, your mild steel or low carbon steel would have had iron and a rust layer. The corrosion product of iron oxide is what I name as rust, which I don't want. But in the case of the Delhi iron pillar, the presence of phosphorus has helped you to form an intermediate layer which now retards the metal dissolution from the surface of the metal towards the environment, or the other way around, retards the movement of environment from the surface towards the metal interface. So the presence of phosphorus has helped it to keep it as corrosion or corrosion free or rust free. Can it work in our environment in Chennai? Or do you say that it will be exactly the same in Chennai? Do you predict that? So corrosion is environment specific. Delhi iron pillar is a rustless wonder. It is perfectly fitting, very nice. It is specific to that environment, but please be sure, or please keep it in mind that it need not, it might still work, I cannot claim it, but need not be the same behavior as we see in the case of Delhi climate. So based on where you use a particular component in an area or an application or in a location, your corrosion process and corrosion forms or corrosion mechanism tends to change as it is in that location. Now, I see here I didn't write only one. I would have written metal and then I would have directly written Fe3O4 or Fe2O3. But I wrote FeOH, I wrote alpha, I wrote gamma, I also wrote Fe3 minus XO4. What does this mean? That I see here, I didn't write in one chemistry alone. I would have written that Fe2O3 or Fe3O4 and finished. So basically what does this say? Based on what the metal, if it is simple iron also, your corrosion product is not as simple as it is exposed to different environments at different conditions, even wet and dry cycle changes, your corrosion product changes from one form to the other form. So understanding iron corrosion itself is a challenging task, and we always say this with this word, rust never sleeps. Why do I say rust never sleeps? Because it keeps changing from one form to the other, and that depends on whether it is in complete dry condition or it is complete wet or it is a cyclic dry and wet conditions. So based on the path at which it goes, the rust chemistry keeps on changing. Therefore, it becomes much more challenging to understand even simple corrosion aspect of iron. Right. I said for iron, the corrosion product is rust. What is the corrosion product on copper? Copper oxide? Okay. Why do I say it patina? This rust is not protective. In the case of Delhi iron pillar, it is protective, but in general cases, rust is not as protective. But when I say copper or copper monuments which you see, we always say it is a patina forming on the surface. Is it protective or non-protective? Somewhat protective. So normally an corrosion product formed on copper alloys, which gives you the greenish color, as we ended up the last part with the European case, where you see that the copper compounds tends to form a greenish color on the surface, which we call it as copper compounds. It could be because of CO2, carbonates, etc., which is basically patina. Those are giving a pleasant appearance, and it is allowing us to protect the metal, base metal, from further corrosion. So we name it as patina. Is there a possible that I can translate that patina to iron? Can I take that patina formation which is adherent on the surface of copper and preventing copper from corrosion, and can I bring into this patina formation on a simple iron based metal? What do I need to do? I have to make it adherent enough. So one such steel which uses this concept of formation of rust, which we also can call it as patina, is called as the weathering steel or the Corten steel. The only thing is the composition which you add to it helps it to be more adherent to the surface, therefore preventing it from failure. Okay. Now, if I have metal and environment, there is an interface layer. So you talked about metal environment interaction. Now we have to have only to understand the strategy to prevent or avoid corrosion. We cannot completely stop corrosion, that's we all know, and we will not attempt to. But what are the strategies available for us to avoid or reduce corrosion? Metal is interacting with the environment. So if I say this as a system, a material and an environment as a system, how can you avoid or try to reduce or retard corrosion? What are the strategies we have? Coatings. So what do you do with coatings? So assume this is my metal and this is my environment. So you did coating. So what is the strategy? You separated the metal from the environment. You avoided the interaction. That is one. So okay, one is strategy is coating. What is the other strategy available? Change the metal chemistry or microstructure. And what is the other available? Change the environment. If I use a silver article, I'm a businessman selling silver. I will not surely sell it in a place where it contains a lot of sulfur and a lot of impurity containing moisture environment. I will try to keep it in an AC showroom, which is as dry as possible and avoid sulfur. The reason is it will form silver sulfide, which we call it as tarnish. So if I look at the base corrosion principle or corrosion explanation itself, I have the strategies involved in it. 1, separate the metal from the environment. 2, if possible, change the metal itself based on its chemistry and microstructure. 3, change the environment or try to keep the environment in your control. So basic 3 strategies for us is only these 3 aspects which we can use for prevention. Okay, this I don't need to say. You all know that no matter what you try, how much of energy we produce from iron ore, we have to give in a lot of energy to get into the metal. This is adding energy, bring into a finished product, it gets back to the same ore. This is what we call it as corrosion cycle. And I always say this, it is nature's way, right? And as he correctly pointed out, I will quickly run through this. If money matters to you, corrosion as well matters, right? So if you be specific with what we saw, it's a recollection of it. We said what corrosion is. We know what the interaction in electrochemical nature. It is environment specific, and he has rightly pointed out corrosion is omnipresent and it's nature's way. We have the task to combat it. If money matters, corrosion as well. Or we have a break now, and then we will meet again in 10 minutes time.